Let's see what is the importance of looking towards the evolution part. So you can see this is a map. Now what this map tells you, okay, if don't get confused if you don't know anything about it right now, but for now just see what and all things are there. There is convolution. So people who are coming from convolution neural network, first of all, when the convolution was introduced, after that only AlexNet came in the picture, right? AlexNet became famous because it's used convolution neural network inside of it, got a good accuracy, and that got famous. Then the above are all other algorithms that got famous. Like you have the technique like color detection, you have edge detection, you have concept like superpixels, histogram, corner detection, and gradients. Using these all things, all other things got invented. So if you see like Sift, the Sift and Hog are both very famous in CV2 library. People do know about it. So before introduction of Sift and Hog, there was invention of histogram method, corner detection, and gradient. Those lead to the introduction of Sift, and Hog was because of gradient. And that's how then next come to BOW, which is also known as bag of visual words. And then Hog also helped us to get into deformable parts model, and BOW comes to spatial pyramid matching. And this is how the web it is. It's not a straight path. Okay, there are many other things which were invented before this RCNN family. Okay, some of you might not have heard about RCNN as well. So RCNN is also very famous for object detection kind of things, but it's not like someone directly invented faster RCNN. Before that, there were huge efforts in efforts in building out this kind of algorithms, and they mapped together these things, and they got the follow-up till faster RCNN. After that, you got other things also. Retina net is there. You have SSDA. What do we have? We have YOLO algorithms as well. Now we have various versions of YOLO algorithms, but this all comes from this only. You should be aware of convolution. You should be aware of this kind of techniques which lead to the to their formation. So now let's be clear with some of the terminologies. What is object classification, object localization, object detection, segmentation? So if you have some architecture which is able to tell you whether the given image is a cat or a dog, it is known as the task of classification. If you have a network or if you have an algorithm which can tell you where that cat or dog is in the image, it is known as localization. I hope you got it. If you don't have bounding boxes, you just have the labels to them, then it is classification. If you have the bounding box, then it is known as localization. If you can do the both of the thing, then you can say it is your object detection. Then what do we have? Object segmentation. For object segmentation, we classify each and every pixel. Okay, if the pixel is belonging to the cat, it will get different color. If the pixel is not belonging to the cat, it will get different color. So this is how the object segmentation is. It's very simple terminologies, guys. If you are able to differentiate between them, it's classification. If you can draw a bounding box around it, it's known as localization. If you can have that bounding box as well as cat as well bounding box as well as the label for a detection, then we have segmentation as well, in which we classify each and every pixel according to their classes. Okay, I hope you guys I hope you all guys get it. Okay, let's start with the problem of detection. Let's say we have this original image which is to the left, and we have another image which is a cropped version of it. And I ask you, how will you find out whether this second image, which is a cropped image, is actually the first image or a part of the first image? So if I ask you this image, is it this image? So like, do you have any idea? Can I see in the comment section how will you proceed? Don't go for any algorithm, but just tell me what will you do. It's segment of image, right? But you can see it, but how will how a computer will see it? How will it know whether this image is a part of this image? Just think of it like, if you think simply, what you can do is you just take this image, you slide it over to, like, you can just take a portion of the original image and just this kind of portion, and you can see whether it is matching or not. If it isn't matching, then just slide it to somewhat right, then again to the right, then again to the right, just slightly to the right, and more and more and more, and you can see that this is matching. and you will say that this image is a part of this image. That means you have detected something, right? You have seen that this image actually belongs to this image, right? But let's say if the problem is not that simple, I have another image which is kind of zoomed as well as cropped as well as rotated image. What will you do? Will you take some portion of this image and then zoom it, then crop it, then rotate it, then again you will slide your window somewhere to the right, then again you will take some portion of the image, then zoom it, then crop it, then rotate it? Now it is too much computational, guys. If you are even into programming, if you can think of it, how much computational this thing can be, just sliding this window and checking whether each of the pixels belong to the same or not, whether they are same or not. And now for now, if I'm moving this thing, I'm like jumping from 10 to 20 pixels at each time. But when you are doing this thing in the computer way, you have to go one pixel each. This is not a good way to do this thing, right? And you get into trouble when the thing is more complicated, like zoom, crop, rotated. Imagine if I change the contrast as well, you won't be able to match the pixel values as well. Okay, and this is what the problem is. What should we do? What can we do? We need to have some intelligence into it for detection. What can we do? So let's move the next thing. What we can do is let's think, like let's take some of the boxes from the image. Like we'll like you can see we have the yellow boxes on yellow color boxes on the image. We can just take those boxes and maybe we could compare these boxes with the image that is given. And if this boxes matches, then maybe we can see that the given image is just like this image. But again, I think this is more computational. This many boxes. How many boxes do we have here? 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 70. Oh man. So you'll compare 70 boxes. Now that also I think is very computational. What intelligence again you can have? Okay. For answering that thing, let's go to one simple exercise that I want you to answer me. So let's say you have this image, you have 6 other small images given, that is A, B, C, D, E, F. And I want you to tell me which this small images, where do they belong to? Okay, I can see some of the responses. Someone is saying train and all, but we don't want to go into that complexities. For now, we are considering that we are just a newbie into it, and we want to see whether with some simple logic can we do it. So tell me, we have this A, B, C, D, E, F images, and so yeah, we can see. Okay, so you can see, you can make a difference, like this E belongs to somewhere like here, F belongs to somewhere like here, C might be coming from here, somewhere from here, and might be D coming from here. And what about A and B? Might be you will say B comes from here, but where exactly from? Might be from here, it can be from here, it can be from here. And A may be from here, maybe from here. But if you see the density, if you see the color, you might say that it comes from the upper right corner. It's more darker there, but where from? Like here, or somewhere from here, somewhere from here. So why is it like we are not able to differentiate this A, B, and we are very much comfortable with differentiating C, E, D, F? Okay, I can see some of the responses. Now tell me something that I want to put light on. What I want to tell you. What do this exercise tell you? You're not able to tell properly where exactly A and B comes from, but right after you see E and F, you can definitely tell that E is from the left corner of the building, F is from the right corner of the left building. Okay, I will tell you the answer. The thing is, those are corners. Okay, this is how our visual system works. We are not that much good into seeing the planes. We are good into seeing corners as well as edges, and that is what we'll take advantage of. We want to take advantage of edges and corners. So if we again, if you're not getting me, let's go to another example. Let's say if you have this first block, blue color block, you have a red colored box into it, and you just shift it to the left, right, and shift to the down. Is there any information inside of it? I guess no. There is none of the information into it. And if you see the same example, what I want to tell you is A and B. If you take it here, somewhere on the top corner, and if you shift it slightly to the right, slightly to the left, it doesn't give you any information. That's why that information is not with you, and that's why you're not able to differentiate those planes, those examples. But if you see the second example over here, if you see this where my cursor is, you have the red box, and if you slightly shift it to the down or slightly to the up, you will have different portions of the blue color into your yellow boxes, right? And this is the information, this is the actual information that your brain interprets. Okay. And if you see to the this this age, there is one red box, and that box, if you move to the left, move to the right, you will definitely get some difference, and that is what information for your brain. If you now the other thing is, if you move this box in the direction of the age, you won't be able to get any information. Take this example. If you have this red color box, if you move it in the direction of the age, you will see the same thing. It's not information for your brain. You want something different into that box. Just like you're doing up and down for this box, you can't have the information when you're moving in the direction of the ages. But what about corners? Let's say this is a corner, and you have this red box that's overlapped. Okay, manage it. And we have this yellow boxes. So yellow color boxes, if you do it up or down, slightly to the right, slightly to the left, you will definitely have separate portions into them, right? And that's what information is. So what we can say is corners are more useful to extract out information. After that, we can say ages, but in ages also, if you move along the age, you won't be able to interpret any of the information out of it. And in the planes, don't talk about it. That's not of any use for now. So we'll make use of this. So where do we start from? We started like, we'll take an image and we'll compare it pixel by pixel. Okay, guys, can you hear me? Because I'm getting the message that my internet connection is poor.
Yes, sir.
Okay.
Yes, sir.
Okay. Okay. So where are we? We saw that comparing pixel wise pixel wasn't good enough. Why? Because if we do the zooming of the image, and if we do cropping, if we do like changing of the color and contrast, then it won't be of any use. But suppose if we are able to find out the edges and corners, those will be more informative thing that we saw out of these two practices. Okay, out of these two exercises. Now let's go back to that image again. Let's say you have an algorithm which provides you with these boxes intelligently. It provided with you some boxes. You can see blue color. Blue color, I guess those are ages. Red color, I guess those are planes. And green color are actually corners. Now you have the choice. You know corners are more important than ages. So to reduce your computation, what you can do is you can remove out this red color boxes. And what do you have now? You have just the green color boxes left. And what do they represent? They represent corners. If you see it properly, just see the eyes, the corner of eye, the corner of mouth, the corner of this design on her sweater, the flower petal, they have the corners into them. Now these are very much unique to this image. Now if someone tells you that I'm giving an image like this, now tell me whether this belongs to here. You don't have to take this image again and slide it over again and again. What you can do is again have this corner detection algorithm applied for this image as well. It will give you this kind of boxes again. Just compare these boxes. No, how many of them are there? 1, 2, 3, 4, 5, 6, 7, 8. Just look for the 7 boxes. If they are same, that means this is the same person, right? Okay, it might happen this is a cropped version of this image, so this box is not there. But after all, you have the control over it. Okay, you can set the threshold. At least you are getting 6 or 7 boxes out of them, 6 boxes or something like that. So you can have that thing. Okay, that will define your accuracy as well for that algorithm. For now, what do we get? So we decided to slide over the image, but we saw that that is too much computational. After that, we saw that if you want to extract out information out of any image, then what is useful? Useful is corner and edges. But someone asks you what is more, what is better which is the best one? That's corner. So you want to find out these corners. For that, you have corner detection algorithms. Using that, you can do it. But again, there is some limitation. Just think of it. Just write in the comment section or chat section. Just tell me, what do you think is missing here? What can go wrong with this technique? Come on, think of it. We are detecting ages. Now, what can go wrong with it? Okay, someone is asking how to find corners in sky pick blue. We don't need to find that blue. That's what I'm telling. That was the exercise to tell you that that wasn't any information part from that image. If we are given the same image, okay. Okay, we don't have any responses. I think people are thinking of it. Okay, let me tell you. What if the image is zoomed? Okay, this is the cropped image. Okay, I didn't tell you. I think I did. You guys should have been recognized it. This is the cropped image of the first image, and that's why your corner are detected. What if the situation is like this? Just look at this situation. Let's say the first thing. Where is my cursor? Okay, this thing. This thing is from your first image. You ran your corner detection algorithm on it, and your corner detection algorithm tell you that this is a corner. Okay, and then what happened is someone gave you a zoomed image of it. Now this corner becomes something like this. Now you can see the corner detection algorithm tells you that this is an edge, this is an edge, and this is an corner. And if you compare them, you won't be finding the similarities, right? This won't be equal to this thing. Now things have gone wrong, right? What you started with, you said corner detection algorithm will help you out, but what if it is zoomed? Though it will be like it will perform well even if you change the colors and all, like if you change the contrast and brightness. But what if it is zoomed? It won't help you out, right? So what you can do now, you want something else. Okay, now we want something else. What is that? Sliding didn't work for us. Corners didn't work for us, not that well if the image is zoomed. And the next option we have is feature descriptors. So what is feature descriptors? This thing is like something which will change whole scenario. Okay, this is the base of your CV2. Now most of you might have heard about CV2 library. It is a very famous library, computer vision library, in which you have some supports of this kind of algorithms which are known as feature descriptor algorithms, which will find out something which will be so useful that you can't even imagine, which shaped our future, like where we are right now. Okay, so what is this thing? What this will do is it will take small image patches. Image patches is what, say your algorithm detected this patch, right? Now what it will do is it will take that patch, it will do some mathematical operation, and it will transform it into something known as feature vector. If someone of you are from CNNs or convolutional neural networks, you might be aware of what is feature vector. Given an image, if you pass it through the algorithm, it will provide you with some vector, a 1D vector, which is too much useful, which brings out the information of that image. Okay, and that's what these feature descriptors are used for. It won't make any sense to look it with our naked eyes. It won't be making any sense for us, but it will make sense for something which is known as SVM. Now, if you are not aware of SVM, I will highly suggest you learn about SVM. SVM is very much useful into machine learning area, and it is used for finding out such kind of pattern recognition things. So what is the task now we are framing is, we'll use this feature descriptor, something known as feature descriptor, which will give us feature vectors. We'll feed this feature vector to SVM, which is known, which is also abbreviated as support vector machine. And the support vector machine will tell us what is this object is. Okay, is it the same object? Is it a dog? Is it a cat, or all? That thing will be managed with support vector machine, but the feature descriptor will find out the important features out of that image, whichever is feed to it. So let's move further to it. Okay, do remember these all things. What and all we got wrong. One slight question to you guys. What do you think was the year when corner detection algorithms were invented? Just think of it. How old can this technology be? We have seen corner detection, no? So what do you think, in which year might this like approximately this thing might be old of? 1990 someone has written, and that's good, right? Even I have written this thing into the slide, 1988. So you can find some papers which tell you like it's from 1980s, dude. So just imagine how sacred it is, right? You should be like studying regarding it. Start to study, start to know about this kind of algorithms. Okay, these are like backbones of our object detection algorithms. They have supported us. After that, we have some advancements as well, and those are like feature descriptors. So let's move on to feature descriptor. What are this? So one of them is known as Sift, scale invariant feature transform. Now we are not going to go into equations and all those kind of stuff. I want you guys to be aware of it. So I'm going to tell you, I want to make you guys aware of these things. Like this kind of things also exist. Okay. Okay, so we had this algorithms of corner detection like 1988, right? And now in 2004, somewhere close to it, someone introduced us with Sift, scale invariant feature transform. Now, what is the specialty of it? Just look at this first example. Just look at towards my cursor. This is an image, and this is the same object you can see. Just the background is different, orientation is different, as well as contrast is different. Everything is different, I can say. Just the object is same. But the Sift algorithm is able to find out the features out of that first image and is able to match with the features of the second image, even though it is rotated, even though the color is changed, even though the background is changed. It can match 5 out of 3 features out of it, right? Maybe the 2 are not detected because they are too small for the second image to detect. But this is how robust Sift is. Sift is able to nullify those rotation, nullify those background and all the scaling things. The second example, how strong Sift is, I want to make you guys realize of is, just see this example. These are 2 images, separate images. The first image is somewhat like zoom out image, and the second image is zoomed in image. You can see color difference as well. Color of background is different. You can see a shadow over here, right? A shadow here. The shadow is not present over here. Now look at the beauty of this Sift algorithm. It is able to match them. Even it is able to draw the lines and match them together. How strong it is, right? Even though the background is different, even though the zooming scale is different. Okay. So guys, unmute only if you have some doubt. Yeah. So what we were looking at is Sift, how good it is, right? We have seen the problems with shifting. We have seen the problems with corner detection. Now this algorithms comes in 2004 and we change whole thing. It is invariant to all this kind of thing, invariant to rotation, invariant to scaling, invariant to background, invariant to image brightness and contrast. So I will highly appreciate if you guys go and read about this thing. This is very much good to know. These are very extensively used using CV2 library. You have support over there also. If you want to see, you can go through some YouTube videos and learn how to use it and practically use it. Okay. Let's move for next thing. Okay, look at this also, this application of Sift. You have seen the first image. You can see the image of a box which is at different orientation, and second image which is at different area. Okay, we have some comment whether shift algorithm. Okay, we'll look at the comment afterwards. Let's focus on the PPTs first. Okay, so we can see that the first image having a different orientation of the box, and second image having the straight orientation. You can see how it is able to match them, right? How strong it is to match them out. Even if the scale is different, even if the orientation is different. This is all because of the one thing, that is corner detection, as well as robustness to the scaling thing, right? Robustness to change in the contrast and color. Okay, so what next? Next is HOG, the histogram of oriented gradients. Guys, this is also another thing which is which you might be which I want you guys to know about. If you're gonna study, do study about Sift. After that, come to HOG. HOG is very much famous. Now this thing also makes use of that only. It is something like the maths is different, but at the end, it is also trying to find out edges as well, edges and corners. So what it makes use of is it finds out the magnitude of gradient as well as finds out the direction in which that gradient is. So let's take an example. Just see over it. Let's say we have this black color which is having value 0, and we have this gray color which is having 50, white color having 100, and this is slightly to the gray side which is 25. Now how will you find the gradients? What does gradient means here? I want you to have the intuitive understanding behind it. We won't be going to the equation. I don't want to bore you out, you guys. Let's go inside of it. So what is it? So let's say we have the direction in this side. You have a value 0 and you have value 100. So what will your gradient be? Your gradient will be 100. If you have something, your sliding window here, and if you move it slightly to the right, slightly to the left, you won't be getting any gradient. It will be 0. Similarly, when your box is here, it will be 0. Similarly, when it is here, it is 0. And if it is inclined, if you're finding a gradient 40 to 45 degree over here, it will be also nothing. So if it is like this angle, which is 90 degree, which is perpendicular, and if you move from the darker section to the whiter section, you can see the gradient is 100, right? And this is something which is telling you ages, right? Here we don't have any age, we have an age here. So this is how Hog works. It also finds out the same thing, ages as well as your corners, but something in different way. You have to go through the maths of it. And if you want to understand more about it, you can, whenever I share this PPT, or will drop this links as well after this lecture. So this is what the histogram of oriented gradient is. It will also find out edges and corners only. So if you want to have, if you want to see the example of it, let's say this is an image, and if you pass through the algorithm, what it will detect is edges. So how is it detecting edges, if you'll say? So let's say if this is a corner, right? And this is also a corner. If you see, this is a corner, this is a corner. If you see its representation after Hog, you can see this thing different than this thing, right? This is different than this. If you see this age and this age, this is also different. And so the representation is also in different orientation. So something is there, right? Some information is there which is telling you orientation, like which is telling you ages, which is telling you corners as well. These two corners are different corners, and that's why you have different representation for them as well. So all the things boil down to one thing. You want ages as well as corners, and those will be feature descriptors for you. After you get this feature descriptor, you can have a use of SVM. Of course, through your eyes, you are able to differentiate it, but for a computer, it won't make any sense. For that famous algorithm known as SVM, it will be used for it. And if you want to see one more example of it, you can see this man. If you do this Hog kind of thing on it, you will see that it is able to extract out the ages out of it, right? And different type of ages, different type of corners are getting different type of notation for it, right? Okay, and when was this invented? This was like 2005. So where we started 18 something, we came to 2002, then we came to 2005. Okay, now moving forward. Okay, this is the assembly. What you have an image, pass it through Hog feature detector, it will detect out the feature, and now you have to provide it with to the SVM detector. Now people who are not aware of SVM, do take a note of it. You guys should read about SVM. It's very famous in machine learning area. Okay. And if you guys want to read about more about it, these are the links. You will be having it. Okay, so over and all, what do we have? We have an image. We want feature out of it. What kind of feature is that? That is a corner, that is the edge, that who will extract them out for you? That is Hog, Sift, or something, some other algorithms like them. So you have Har, Cascade, some other algorithms are also there, which will help you out to extract out these features. You just flatten them out and you just provide it to the SVM support vector machine, and it will do the helpful things for you for the classification purpose. Okay, so what do we have now? We have seen some basic ideologies which could be useful for detection of an object in an image, and we got to know what are the things behind it. We started with sliding and we came to edges and corners, and we came to know that there are some algorithms which will be helpful for you to extract out this kind of features. Those will be fed to SVM, and SVM will do the required thing for you for the classification purpose. Now let's see the whole scene, okay? The whole scene where deep learning came and where these guys were. So if you can see here, there's my cursor. Okay, so this was year 2010, this was year 2011. So this was the competition. So this is whatever you can see, ILSVRC, this is the name of data set. Don't get confused with it. Just imagine this is the year 2010, this is the year 2011, and there was something on which it was used to be tested on, this kind of algorithm, how good they are. So what happened was, this 28.2 take is as error rate. So this was the error rate if you guys use Sift, Hog, or something known as Surf, ORB, or Voila Jones or Har Cascade kind of things for extracting the features and passing them to SVM for your classification kind of thing. So the error rate which you were incurring was 28.2 or 25.8, something like that. Now the change came where deep neural networks started to come into picture. So AlexNet. So things for convolutional neural networks come into picture, like come into light for all the research people when AlexNet got popular. And why it got popular, you guys know, right? Convolutional operation, what it supports. So using convolution operation, we got this convolutional neural networks, and AlexNet was one of them who was using it, and he got pretty much good accuracy. You can see the jump, right? 25 from 25 it came to 16, something like 9% drop, right? And this is why the people got excited about it. This is why they started to see towards it. What is deep learning? What is it? And slowly in 2013 we got one more network which was 8 layers. Then we got something like VGG 16, VGG 19, this kind of architectures came into the picture, which were like 19 layers deep. And the error rate again came down to 7.5. Don't get confused with all these notations, okay? I will tell you guys what these are, but for now just follow me. So we had an error rate of something close to 28.2, which dropped to something like small, but it wasn't that much exciting. But when it dropped by 9%, people got excited. Now let's see what is this deep neural networks, why they are performing this good. And when we come to 2015, so ResNet was there and it performed so well, like where it started from 28.2, it came down to 3.57. So that's very minimal, right? And that's where that excites you to know what it is. How is the accuracy so good? This is the error rate, okay? Don't get confused with the accuracy. This is error rate. So it's amazing, right? But the layers were deep. Now it started with 8 layers and it went up to 152 layers. Now 152 layers that's why it's known as deep network, okay? And that's where the name come into the picture, deep neural networks. Now the problem is, what should you go for? Whether should you go for a classical CV2 approach, which is your Sift and Hog, which extracts out the corners and which help you out for classification, or should you go for this kind of deep networks? They are giving you pretty much good accuracy, but what is the thing that that might be disadvantage with it? So the one first thing that comes into the picture is size. So okay, if you go for something like this Sift and Hog feature detector, you might end up with an algorithm which will just take 4 KB of size. And if you go for something like this deep network, like ResNet network, which was introduced in 2015, so that took like 152 layers, and for 152 layers, it used to take 25 million parameters. Now, if you want to save this 25 million parameters, it takes 100 MB size. And to train this kind of algorithms, you need GPU, and that is heavily computational. And what if you want to deploy this thing into your edge devices? Now, what is edge device? Edge device can be your cell phone as well, or you can say your computer. Now you can't have this big size for application into your cell phones, right? 100 MB and all. Like you want to reduce it, right? You want a good accuracy as well as you don't want to take it this much amount of size. So if your application is something which is not that much computational, which does not require that much computation, and your edge device is not that much computationally good, you can go for classical CV2 approaches. Yes, error rate is more, but that is manageable with the size. Yeah, you can see 100 MB, and what is 4 KB, right? It's too much less. So it's your thing. Again, it depends on your application. Okay. The one thing that you will be compromising is the accuracy. Now, one more thing, which is disadvantage with this deep neural networks are, there is famous saying, what you think your model is learning and what your model actually learned, it's not same. Okay, so if you think your model is learning something, it won't be same what do you think. Okay, it won't be like you think the model is thinking this, learning this thing, and it will be learning that thing. There was one of the study, so I will take that example. There was one study in which they want to classify whether a tank is in forest or whether the tank is in open area. They created the data set. They had 100 images for tank which was in the forest, and they had 100 images of tank which was in open area. Now they tested it on your testing data, and they got very much good accuracy. Now they were amazed with it, like how can it perform so well. Now they collected again some more data and they tested on it. Now what the thing came into picture is the deep neural network had nothing to do with the structure of a tank. That is my cursor. Okay, so you can see this is the structure of a tank, right? But the network didn't learn it. What it learned was just to see whether it is a sunny day or whether it is a cloudy day. Now come on, you don't want it to happen, right, with you. So you should be aware of all these kind of things a network can go bad with. There's one more example in which there was one study to detect whether the cell is you have this study, right, detection whether it is a malignant or benign cancer cell detection. So in that there was one study in which they had two samples, two different types, malignant and benign. And in malignant, they used to have a scale which used to tell how much is the length of that tumor, how much is the size of the tumor. And in benign one, they didn't had it. And they trained the model, and they were also getting a good accuracy. They again got some more data and they tested on it. And what they came to know is the model didn't learn anything about this cells. It just learned whether there is a scale or not. If it is having a scale, it was classified as malignant, and if it is not, then benign. So come on, you don't want it to happen, right? So if you're going for this kind of architecture, deep architecture, you should be aware of this kind of outcomes as well. It's not what you think the model is learning always. Okay, but contrast to that, if you come to this classical approaches, these are handmade feature extractors. You know what kind of features are being extracted out of that image. If you read more about this kind of Sift, Hog, and Har cascade kind of algorithms, you will come to know that the feature extractor are hand engineered. They are not kept on on luck. Okay, here you are on the luck whether the model is learning that or not. You have to do many iteration, you have to do many experiments to find out whether the model exactly learned what you wanted. So these are the two things which you have to keep into mind. If you go for deep networks, you don't know what they are learning. If you go for the this shallow kind of network, these are known as shallow networks. Okay.